A telescope in the constellation Leo, 120 light-years from Earth, has discovered something that will revolutionize our understanding of life in the cosmos. The James Webb Space Telescope has discovered a world where the temperature hovers at exactly 120 degrees Fahrenheit, and the atmosphere vibrates with the chemical signature of living organisms. Scientists are 99.7% convinced they have discovered it. Like and subscribe to a planet brimming with life that is more habitable than Earth. Prepare to witness humanity's greatest discovery. We begin. The data. Arrived on a Tuesday morning in December, buried beneath gigabytes of infrared light. Niku Madden, captured by humanity's most powerful eye in space, sat at his computer screen at Cambridge University, seeing wavelengths of light traverse 120 light-years to Earth. What he saw caused his palms to quiver. There was an unusual signal in the spectrum of light filtered by an extraterrestrial atmosphere. Dimethyl sulfide, a chemical created on Earth solely by living things, was not just a trace, but a signal so strong that the chances of it being a mistake were less than 3 in 1,000. The James Webb Space Telescope had discovered what every scientist had hoped for. There is undeniable evidence of life beyond our solar system. The planet K has two 18b orbits around a red dwarf star in the habitable zone, which allows liquid water to exist. But this world is unlike anything else in our solar system. 8.6 times the mass of Earth, enveloped in a hydrogen-rich atmosphere that generates such a perfect greenhouse effect that enormous oceans remain liquid beneath alien skies. The temperature readings were astonishing. 120 degrees Fahrenheit. Warm enough to support life, but chilly enough to prevent complete evaporation of water. Malu Sudan's team had been watching this world for months, using JWST with amazing sensitivity to peek through the planet's atmosphere as it passed in front of its star. Each transit uncovered fresh secrets. Water vapor was detected first, followed by methane, and finally carbon dioxide. But dimethyl sulfide was a game-changer. A chemical so inextricably linked to biological processes that finding it in a foreign environment was like to uncovering a neon sign advertising life. The implications struck him like a physical punch. If confirmed, this finding would finally put an end to humanity's cosmic loneliness. We would not be alone in the universe. The probability estimates were startling, with 99.7% confidence that the signal was genuine and not noise or pollution. This level of confidence was unusual in an astronomical field where certainty is rare and findings are sometimes overturned. But K218b wasn't just any world. Its distinct features made it possibly more habitable than Earth itself. The hydrogen atmosphere works as a giant blanket, trapping heat and maintaining stable conditions on the planet's surface. Unlike Earth's narrow nitrogen atmosphere, this thick envelope of hydrogen might maintain liquid water over a considerably wider temperature and pressure range. The star K218 is a red dwarf, which is smaller and cooler than our Sun but far more stable. While our Sun will eventually develop into a red giant and destroy all life on Earth, red dwarfs burn for trillions of years, giving steady energy for ages. Any life that arose on K218b would have almost infinite time to create complexity beyond our comprehension. As Madhu Swan prepared to present his discoveries to the world, he recognized that December morning would be remembered as the time everything changed, the moment humanity realized it wasn't alone. But this was only the beginning of a story that would fundamentally alter our understanding of life, the cosmos, and our place in it. Scientists once believed that humanity needed to find Earth's twin, a rocky planet orbiting a sun-like star at the ideal distance for liquid water. K218b broke that assumption totally. This world demonstrated that life may originate in situations so strange that we never thought to look for it. The planet is classified as a super-Earth, meaning it is larger than Earth, but smaller than Neptune. Until recently, scientists dismissed these planets as hostile gas balls too large to support life as we know it. K218b required scientists to totally reinvent what a livable world would look like. Its bulk generates surface gravity that is roughly 3 times stronger than Earth's, An individual weighing 150 pounds on Earth would weigh more than 400 pounds on K2-18b. However, this crushing weight may actually improve life. The strong gravity maintains the atmosphere in place, preventing it from escaping into space, as Mars did billions of years ago. The atmosphere contradicts all of our assumptions about habitable worlds. Instead of oxygen and nitrogen, we breathe. The atmosphere of K2-18b is dominated by hydrogen and helium on Earth. Hydrogen is a trace gas that accounts for less than 1 part per million of our atmosphere. On K2-18b, hydrogen makes up the vast bulk of the atmospheric envelope, resulting in a wholly foreign environment. This hydrogen atmosphere produces what scientists refer to as a runaway greenhouse effect, but in reverse. Instead of heating the globe like Venus, hydrogen works as a perfect insulator, keeping temperatures consistent over the planet's surface. The thick atmosphere efficiently redistributes heat, so that even the planet's night side, which never gets sunlight, remains warm enough to support liquid water. The chemical signals identified by JWST offer a picture of a planet in which life not only exists, but thrives alongside life, showing dimethyl sulfide. The atmosphere contains methane, carbon dioxide, and water vapor, a combination of chemicals that suggests active life activity on Earth. Bacteria, as well as complex creatures, create these gases, creating a planetary metabolism that can be observed from space, but perhaps most surprising is what is absent from K2-18b's atmosphere. A shortage of ammonia, a chemical that would dominate if the planet were a dead gas giant, gives compelling evidence that organic processes are actively eliminating it from the atmosphere. Life is not only existent on this planet, it actively shapes its atmosphere and chemistry. The finding of K2-18b reveals that the universe could be teeming with life in unexpected locations. Look, if life can originate and thrive in a super-Earth's hydrogen-rich atmosphere, the number of potentially habitable worlds in our galaxy may increase by hundreds of times. Estimated red dwarf stars such as K2-18, which account about 3/4 of all stars in the galaxy, have suddenly become excellent targets in the search for extraterrestrial life. The ramifications are startling. We may not be searching for Earth's twin after all. We could be looking for Earth's weird cousin, surviving in conditions so unusual that we're only now starting to fathom them. The James Webb Space Telescope is not only humanity's most powerful space observatory. It's a time machine that sees further into the universe than any device ever created. Floating 1 million miles from Earth at a gravitational equilibrium point known as L2 Webb, there is continuous darkness. Its huge sunshield blocks heat and light from our star, keeping its equipment cooler than Pluto's surface. A telescope's primary mirror is 21 feet across, nearly 3 times wider than Hubble's, but size alone cannot explain the Webb's revolutionary possibilities. The mirror is made up of 18 hexagonal segments, each coated with a tiny layer of gold that reflects infrared light with unparalleled precision. When these pieces combine, they form a mirror that is so well aligned that it can detect the heat signature of a bumblebee on the moon. Human eyes cannot see infrared light, yet it is essential for discovering life on other planets. When planets pass in front of their stars, a small amount of starlight passes through their atmospheres. Before reaching Earth, many substances absorb specific wavelengths of infrared light, leaving distinct fingerprints that the Webb can identify with remarkable sensitivity. The difficulty of identifying these chemical markers is practically inconceivable. Imagine attempting to see a firefly hovering next to a brilliant searchlight from 1,000 miles away. K2-18 is billions of times brighter than the planet that orbits it. However, Webb can detect the weak infrared glow of molecules in the planet's atmosphere with pinpoint accuracy. Webb's secret weapon is coronagraph technology, which was initially supposed to obscure starlight and show items hidden within it. Glare's sophisticated picture processing techniques remove the overwhelming brilliance of the star, leaving only the weak infrared traces of atmosphere molecules. It's like employing a clever filter to eliminate the roar of a jet engine so you can hear a whisper underneath. Detecting dimethyl sulfide on K2-18b required Webb to work to its absolute limits. The molecule emits a modest infrared signal that required several observations over several months to prove its presence. Each observation collected only a few photons of light that had traveled 120 light-years over space, containing information about life on another planet. But the Webb's greatest astounding feat may be its capacity to track temperature with incredible accuracy. The telescope discovered that K2-18b maintains a surface temperature of precisely 120 degrees Fahrenheit, warm enough to support liquid water, but chilly enough to prevent full evaporation. This temperature reading, accurate to within a few degrees across interstellar distances, marks one of the most exact observations yet taken of an exoplanet's environment. The data processing required to extract these insights from raw infrared observations requires some of the most powerful computer algorithms ever created. Artificial intelligence algorithms sift through millions of data points in search of patterns so subtle that human observers would miss them. The discovery of life on K2-18b is more than just a technical accomplishment. It also demonstrates humanity's ability to push the limits of what is conceivable. Webb has drastically altered our relationship with the cosmos. We are no longer simply speculating if life exists elsewhere. We're closely monitoring it. Breathe at 120 degrees Fahrenheit. The number is almost too perfect to be genuine. It's the heat of a hot summer day in Death Valley, the comfort of a relaxing hot tub, or the heat of a fevered human body fighting an infection. On K2-18b, the temperature is what allows life to exist on a global scale. Temperature is everything in life. Too cold and water turns into ice, which cannot support complex chemical reactions. Life demands too much heat, and water boils away into steam, leaving behind a barren desert, the range within which liquid water can exist. The habitable zone, as scientists refer to it, is shockingly tiny. Earth is almost exactly in the center of this zone surrounding our Sun, a cosmic accident that enabled life to flourish over billions of years. But K2-18b's perfect temperature is not a coincidence. It is the outcome of a complex equilibrium between solar energy and atmospheric chemistry that produces circumstances more stable than those seen on Earth. The planet orbits its red dwarf star at a distance that allows it to receive about the same amount of energy per square meter as Earth does from our solar. This cosmic coincidence indicates that despite being 120 light-years away, K2-18b resides in roughly the same thermal environment as our own planet. The hydrogen atmosphere is essential for sustaining this ideal temperature. Unlike Earth's thin nitrogen atmosphere, which allows heat to escape quickly into space, K2-18b's thick hydrogen envelope functions as a planetary blanket. The hydrogen molecules trap infrared radiation, forming a greenhouse effect that keeps the planet warm, even on the night side, which never gets sunlight due to the planet's locked spin. This steady temperature produces an unparalleled situation in our solar system, a planet in which liquid water can exist at all times, from the eternal day to the eternal night. On Earth, temperatures vary from day to night. The summer and winter holes, as well as the equator, provide complicated weather patterns and climate zones on K2-18b. The thick atmosphere efficiently redistributes heat, allowing the entire planet to maintain a steady, life-friendly temperature. The ramifications for life are startling. Temperature variations on Earth stress living species, requiring them to adapt to seasonal changes and migrate in order to survive the winter. Alternatively, develop complicated physiological processes to regulate their interior temperature. On K2-18b, life would not present such challenges. The steady temperature would allow organisms to focus their energy on growth, reproduction, and evolution rather than survival. Perhaps most remarkably, the 120-degree temperature on K2-18b falls inside the range where life as we know it can not only exist but thrive. Laboratory investigations have demonstrated that biological systems may function successfully at temperatures as high as 250 degrees Fahrenheit at 120 degrees. Chemical processes occur quickly enough to sustain complicated metabolism, while keeping cool enough to avoid the destruction of key biological substances. The finding of K2-18b's ideal temperature is more than just a scientific curiosity. It demonstrates the universe's ability to produce conditions conducive to life that are not only habitable, but possibly more so than Earth itself. In a universe where most planets are either freezing wastelands or molten hellscapes, K2-18b stands out as a beacon of hope, a world where life not only survives, but thrives in complete comfort. Dimethyl sulfide may sound like a chemical tongue twister, yet these three words represent the most significant discovery in human history. When the James Webb Space Telescope spotted this molecule in K2-18b's atmosphere, it discovered something that no known non-biological process has ever generated. It discovered the signature of life itself on Earth. Dimethyl sulfide is only created by living organisms. Phytoplankton in our oceans produce this molecule as a byproduct of their metabolism, releasing it into the atmosphere, where it influences cloud formation and weather patterns. Dimethyl sulfide is also produced by marine bacteria, certain types of algae, and some plants as part of their normal biological processes. But there is no geological process. There's no chemical reaction. No non-living system has ever been seen producing this chemical. The discovery of dimethyl sulfide on K2-18b is significant because it represents what scientists call a biosignature, a molecule that can only be formed by life as opposed to oxygen, which can be produced by non-biological processes, or methane, which can seep from geological strata. Dimethyl sulfide has no recognized abiotic origin. Its presence in K consists of 2-18bs. The atmosphere is as close to proof of life as we can come without seeing the organisms that make it. The molecule's chemical structure reveals biological complexity. Dimethyl sulfide is made up of sulfur atoms bound to carbon-bearing methyl groups, a combination that requires particular enzymes to form. These enzymes evolved on Earth over billions of years as part of the sulfur cycle, which helps regulate our planet's atmospheric chemistry. The presence of identical compounds on K2-18b shows that life has evolved sophisticated biochemical processes, perhaps the most stunning part of the discovery. The quantity of dimethyl sulfide in K2-18b's atmosphere. The amounts found by Webb are orders of magnitude greater than what would be expected of a planet just starting to generate life. This shows that biological processes on K2-18b are not only existing, but thriving on a global scale. The ramifications are astounding. If life on K2-18b emits dimethyl sulfide at quantities detectable from 120 light-years away, the biosphere must be huge. We're not talking about minuscule organisms trying to live in isolated regions. We're talking about a massive and productive planetary ecosystem that is actively altering the chemistry of the entire world's atmosphere. The revelation raises important issues regarding the essence of life itself. If creatures on K2-18b produce dimethyl sulfide, they must have evolved metabolic pathways comparable to those found on Earth. This implies that the fundamental chemistry of life, the utilization of carbon, hydrogen, oxygen, nitrogen, and sulfur. It is possible that the ability to construct complex molecules is ubiquitous. Life may not be very common in the cosmos. It may follow predictable patterns wherever it emerges. The discovery of dimethyl sulfide is more than just a scientific accomplishment. It is the moment when humanity realizes that we are not alone in the universe. Somewhere 120 light-years away, amid alien sky and in hydrogen-rich atmosphere, life breathes, grows, and fundamentally alters the chemistry of the entire planet. For the first time in human history, we have proof that life exists beyond Earth. In the field of science, certainty is a rare and valuable asset. Scientists speak of probability and statistical confidence levels. Additionally, there are error margins. They hedge their bets, temper their remarks, and accept uncertainty. However, when the James Webb Space Telescope data on K2-18b was evaluated, the figures revealed a story so apparent that even the most conservative scientists could not deny it. There was a 99.7% possibility that the dimethyl sulfide signal was genuine. To understand what this means, consider flipping a coin 1,000 times. The likelihood of receiving heads or tails on every one flip is 50%. but the probability of getting heads 997 times out of 1,000 flips is so minuscule that it would never occur by chance in the history of the universe. That is the statistical confidence with which scientists believe they can identify life on K2-18b. The confidence level is derived from a complex statistical technique known as sigma detection in particle physics and astronomy. Sigma levels are used by scientists to determine the likelihood that a signal represents a meaningful finding rather than random noise. A 3 sigma detection indicates that the signal has a 99.7% likelihood of being real. It's a 3 out of 1,000 possibility. This is a false alarm. This is the same statistical threshold used to detect new subatomic particles, confirm the existence of gravitational waves, and validate the most significant discoveries in modern physics. However, achieving this level of certainty in an extraterrestrial atmosphere needed remarkable precision. The dimethyl sulfide signal is extremely feeble, only a few parts per billion in the infrared range. To detect it, the Webb had to measure light wavelengths to 1 part in 10 million accuracy, which is equivalent to detecting the width of a human hair to the precision of a single atom. The investigation comprised several months of independent observations, each of which confirmed the presence of the dimethyl sulfide signal. Different Webb-based devices discovered the same molecular fingerprint at various wavelengths, providing redundant confirmation of the discovery. Computer algorithms sifted through millions of data points, looking for systematic flaws or contamination that could explain the signal. None were discovered. The statistical analysis also looked into potential causes for the signal. Could it be due to unknown air chemistry? Could it be contamination from the Earth? Could that be a result of the telescope's instrumentation? Each possibility was thoroughly explored and ruled out mathematically. The only plausible explanation for the results is biological synthesis of dimethyl sulfide by living creatures on K2-18b. This level of assurance is nearly unique in exoplanet research. Most discoveries of atmospheric chemicals on other worlds are reported with far lower confidence levels, frequently failing to meet the criteria for publication in scientific publications. The 99.7% confidence in the K2-18b biosignal signifies a significant improvement in our ability to discover life beyond Earth. The consequences of this statistical certainty go far beyond astronomy. When scientists declare they're 99.7% certain that life exists on K2-18b, they're making a statement as true as any other. In science, it is as certain as the presence of DNA, as solid as the theory of relativity, and as old as the cosmos itself. We no longer question if there is life elsewhere. We know it does. Under the strange heavens of K2-18b lies an ocean. Unlike everything else in our solar system, it is composed of water combined with hydrogen at pressures that would shatter any Earth-based living form. However, this hydrogen ocean could be the most life-friendly environment in the known cosmos. The peculiar atmospheric chemistry of K2-18b is responsible for the existence of the ocean. The planet's hydrogen atmosphere does not simply float above the surface, it melts into liquid water, creating a solution that is stable across a significantly larger temperature and pressure range than pure water. This hydrogen-water mixture can remain as a liquid at temperatures ranging from near freezing to over 300 degrees Fahrenheit, providing life with a wide range of circumstances to thrive on Earth. The deepest sections of our seas are under nearly 1,000 times more pressure than the surface. Most life forms cannot survive at these depths because the pressure would collapse their cellular structures. However, on K2-18b, the hydrogen in the water functions as a natural pressure buffer, allowing the liquid to retain properties similar to water at much lower pressures, even at deep depth. The hydrogen ocean also addresses one of the most significant barriers to life on exoplanets: air loss. Earth's atmosphere is gradually disintegrating into space, and in a few billion years, our planet will be as airless as Mars. However, K2-18b's hydrogen ocean operates as a vast atmospheric reservoir. As hydrogen is lost to space, more dissolves from the ocean to replace it, potentially keeping the atmosphere constant for trillions of years. The chemistry of this hydrogen ocean creates possibilities for life that do not exist on Earth. Hydrogen may be used as an energy source for biological activities, allowing creatures to breathe the ocean itself on Earth. Certain bacteria can metabolize hydrogen. They are limited by its paucity in our atmosphere on K2 18 billion. Hydrogen-breathing organisms might flourish in an environment where their major energy source is virtually limitless. But perhaps most surprisingly, the hydrogen ocean could support life forms that are utterly invisible to our traditional detection tools. Traditional searches for life focus on creatures that produce oxygen, such as plants and algae. However, on K2 18b, the primary life forms could be hydrogen-metabolizing organisms with very distinct chemical signatures. Webb found dimethyl sulfide, which could be one of many biosignatures in an alien environment based on hydrogen chemistry. The ocean's depth remains A. Computer models indicate that it could be hundreds of miles deep, far deeper than any ocean on Earth. This massive volume of liquid water combined with hydrogen might support ecosystems of unprecedented complexity and diversity. The consistent temperature and pressure circumstances may allow life to evolve in ways that are not feasible on Earth, potentially reaching levels of complexity beyond our imagination. The finding of K2 18b's hydrogen ocean marks a significant shift in our concept of habitable environments. We are no longer hunting for worlds like Earth. We are hunting for worlds that may be superior than Earth. In the hydrogen oceans of super-Earths orbiting red dwarf stars, life may not only survive, but flourish in ways that make Earth's biosphere appear constrained. By contrast, the universe's most life-friendly settings may be the most alien to human experience. The atmospheric chemistry of K2 18b seems like science fiction, but it's real and stunning. While Earth's atmosphere is a basic combination of nitrogen and oxygen, K2 18b's atmosphere is a complicated concoction of molecules that generate conditions that are both foreign and strangely familiar. Methane flows through hydrogen clouds, carbon dioxide creates crystalline structures in the high atmosphere, and, under certain conditions, carbon atoms compress into diamond showers. The methane in K2 18b's atmosphere narrates the story of ongoing biological activities on Earth. Methane is created by a variety of sources, including bacteria, marshes, and cattle digesting grass. It is one among the most prevalent byproducts of biological activity, but it is also extremely reactive, breaking down in the atmosphere in a few decades. The fact that Webb detected significant amounts of methane on K2 18b indicates that something is actively producing it in large quantities. However, methane on K2 18b serves a purpose other than just being a byproduct of life in the hydrogen-rich atmosphere. Methane is an important component in the carbon cycle, helping to regulate the planet's temperature and atmospheric chemistry. Organisms on K2 18b could actually breathe methane and use it as an energy source in ways that would be unthinkable on Earth. The atmospheric pressure on K2 18b generates conditions that would appear miraculous to Earth-based observers at certain altitudes. The pressure and temperature are just right to compress carbon atoms into diamond crystals. These small diamonds originate in the high atmosphere and then drop down to the surface, creating a steady shower of exquisite gems. But for the life forms on K2 18b, these diamonds may be as common as raindrops are to us. The presence of CO2 in the atmosphere complicates the planet's chemistry. Unlike Earth, where carbon dioxide is a trace gas, K2 18b's atmosphere includes significant levels of CO2, which interacts with hydrogen and methane in complex ways. This three-way chemical dance generates circumstances that could sustain completely different types of photosynthesis than anything discovered on Earth. The atmospheric dynamics on K2 18b are dictated by the planet's locked rotation, with one side always facing the star and the other in continuous darkness. This generates vast air currents that transport heat, moisture, and chemical substances from daytime to nighttime. The outcome is a global weather system that constantly mixes and redistributes atmospheric chemistry, resulting in stable conditions across the whole surface. The dense atmosphere also shields all surface life from dangerous radiation. Red dwarf stars, such as K2-18, are known to emit intense flares that can sterilize planet surfaces. However, K2-18b's dense hydrogen atmosphere acts as a natural shield, absorbing and deflecting radiation that would be harmful to terrestrial life. This shielding may be critical for allowing complex life to evolve and thrive on the planet's surface. The chemical complexity of K2-18b's atmosphere implies that life there could be significantly more advanced than anything on Earth. In a world where diamonds fall from the sky and methane serves as breath, evolution may have pursued pathways that appear impossible to us. The biosignatures recognized by the Webb could be the start of a biochemical story that changes our understanding of what life is. We are discovering life not only on another planet, but also in another universe of possibilities. K2-18 is not a star like the Sun. It's a red dwarf, which is smaller, cooler, and less bright than the star that illuminates our Earth. However, this relatively tiny star could be the most important form of star in the cosmos. It took 4 billion years for basic microorganisms to evolve into the complex ecosystems that we observe today. If life on K2-18b had even a fraction of the time available around its red dwarf star, it might have evolved to levels of complexity and intelligence that would make Earth's biosphere appear primitive. In example, K2-18 is quite quiet compared to some red dwarfs, which are notorious for emitting massive stellar flares capable of sterilizing planet surfaces. These flares can raise a star's energy output by thousands of times over hours or days, hitting surrounding planets with fatal radiation. However, K2-18 looks to be a well-behaved red dwarf with minimal flare activity, allowing its planets to have stable atmospheres and possibly support life. Despite the fact that K2-18 is much smaller and cooler than our Sun, its steady energy output produces conditions that are very comparable to Earth's. The planet K2-18b orbits its star far closer than Earth orbits the Sun, completing one orbit in approximately 33 days. However, because the star is cooler, this close orbit puts the planet in an ideal position to receive nearly the same amount of energy per square meter as Earth does from our Sun. This cosmic coincidence indicates that K2-18b is located in the Goldilocks zone, as defined by astronomers. Not too hot and not too cold, but just ideal for liquid water to dwell on the surface. Unlike Earth, which will eventually be destroyed when our Sun develops into a red giant, K2-18b may stay in this perfect zone for trillions of years, offering an almost infinite timeline for life to form and thrive. The gravitational connection between K2-18b and its star has also resulted in tidal locking, where one side of the planet always faces the star and the other is perpetually dark. This may appear to be a disadvantage, but the planet's vast atmosphere effectively redistributes heat, ensuring that both sides retain acceptable temperatures. The end result is a world with a permanent day, a permanent night, and a variety of environments for life to explore and exploit. K2-18 symbolizes more than just a star. It represents a promise of cosmic stability that has the potential to nurture life far beyond our greatest expectations. The distance to K2-18b is both unimaginably large and tantalizingly close. 120 light-years indicates that the light we see from this world has departed its surface. When Teddy Roosevelt was President of the United States, there was such a huge distance. The fastest spaceship would take nearly 2 million years to get there, but it's virtually next door in cosmic terms. To put this distance into perspective, consider downsizing the entire Milky Way galaxy to the area of North America. Earth would be smaller than a grain of sand, while K2-18b would be another grain of sand, the size of a small town in a galaxy with over 100 stars. Billion stars. K2-18b is close enough for us to investigate its atmosphere in depth, evaluate its chemical composition, and detect signs of life itself. The light that conveys information about K2-18b's atmosphere has traveled through space for 120 years, spanning enormous voids between stars, while carrying the molecular fingerprints of an alien planet. When the light reaches the James Webb Space Telescope's mirrors, It is so dim that it takes hours to detect the presence of a single molecule in the planet's atmosphere. However, distance can be both advantageous and disadvantageous. The 120 light-year journey functions as a cosmic time machine, allowing us to view K2-18b. Dimethyl sulfide signals were detected more than a century ago. We were created by living organisms when the Earth was only beginning to industrialize. We are literally witnessing the breath of alien life from the past. The ramifications of discovering life at this distance are startling. If we can detect biosignatures on K2-18b from 120 light-years distant, then the biological activity on that planet must be immense. The creatures that produce dimethyl sulfide do more than merely survive. They thrive on a global scale, creating atmospheric fingerprints that are strong enough to be detected beyond interstellar space. This distance also makes K2-18ba an ideal target for future observations. While it is too far away for any human mission, it is close enough to investigate in great detail. With increasingly powerful telescopes, the upcoming extremely large telescope with a mirror over 100 feet across will be able to analyze K2-18b's atmosphere with unprecedented precision, potentially detecting dozens of different biosignatures. The 120 light-year distance places K2-18b within what astronomers call the local neighborhood of stars. This region contains thousands of star systems, many of which are expected to have planets. If life exists on K2-18b, it implies that our local galactic neighborhood is teeming with live worlds, each with its own distinct ecosystem and evolutionary path. Perhaps most amazingly, the distance to K2-18b implies that if there is intelligent life on that planet, they may be detecting indications of life on Earth right now. The radio signals we've been sending into space for the past century are finally reaching their destination, potentially announcing our presence to any civilization intelligent enough to detect them. We are not simply discovering life on a distant planet. We may be making the first contact across the immense blackness between stars. The challenge appeared impossible. How do you photograph a firefly hovering near a searchlight from 1,000 miles away? That's exactly what the James Webb Space Telescope needed to do to get direct photographs of planets like K2-18b. The star, K2-18, is billions of times brighter than the planet around it, resulting in a glare so strong that finding the planet would be difficult. The solution emerged from an unexpected source, our own sun. For decades, astronomers have used coronagraphs to screen out the sun's blinding glare while observing. Its corona is a faint outer atmosphere that is generally inconspicuous in comparison to the star. Brilliant surface web developers use this technology for exoplanet identification, resulting in what may be the most sophisticated light-blocking device yet created. Webb's coronagraph functions similarly to a meticulously constructed eclipse, consisting of a succession of properly shaped masks and mirrors. Block the star's light while allowing much fainter light from orbiting planets to flow through. However, this is not just a simple disk obstructing the star. It's a sophisticated system of masks, each of which is meant to eliminate a certain sort of light contamination. The tolerances are so fine that a misalignment of a few billionths of a meter would spoil the entire experiment. The coronagraph's performance is measured in something called contrast ratio. Indicates how much fainter the planet is than its star. This ratio for K2-18b is around 10 billion to 1. To put this into context, consider trying to see a single candle burning next to the brightest stadium lights during a night game while peering through a telescope from the other side of the country. The coronagraph simplifies this hard effort, yet concealing the star's light is only half the struggle. Once the starlight has been eliminated, astronomers must deal with speckles, tiny flaws in the telescopes, optics that generate false signals like planets. Advanced computer systems use artificial intelligence to evaluate these speckles in real time, distinguishing between actual planetary signals and visual distortions. The computing power required is astonishing, comparable to analyzing millions of photographs are taken concurrently to pinpoint one single face amid a crowd. The coronagraph's success is predicated on Webb's remarkable stability. The telescope must maintain its position in space with millisecond accuracy, which is equal to holding a laser pointer stable enough to hit a dime on the moon. Any vibration, drift, or small movement would obscure the precise observations, rendering planet detection impossible. Perhaps most amazingly, the chronograph does more than just block light, it actively shapes it. Using a method known as wavefront correction, the system constantly adjusts the incoming light to provide the ideal conditions for planet detection. It's like having a cosmic lens that can bend and focus light to reveal unseen worlds orbiting distant stars. The coronagraph technology that discovered K2-18b is only the beginning of a revolution in exoplanet finding. Future telescopes will use much more advanced coronagraphs capable of identifying Earth-sized planets around Sun-like stars, potentially exposing dozens of worlds with life. But the graph's biggest triumph is not solely technological. It's philosophical. By letting us to see previously invisible planets, it has provided us with a glimpse into the cosmic neighborhood we were unaware existed. When astronomers first computed the mass of K2-18b, they discovered something that called into question everything they believed they understood about planetary habitability. The planet weighs 8.6 times the mass of Earth, making it roughly comparable to Saturn in terms of overall mass. But unlike Saturn, which is a gas giant without a solid surface, K2-18b looks to be a water world with more favorable conditions for life than Earth. On Earth, the link between planetary mass and habitability is complex and counterintuitive. We've come to think of our planet's size as ideal for life, large enough to support an atmosphere but tiny enough to sustain a tolerable surface gravity. However, K2-18b demonstrates that bigger can really be better when it comes to hosting life over cosmic timeframes. The planet's immense size results in surface gravity that is nearly 3 times stronger than Earth's. While this may appear to be a disadvantage, the intense gravity actually improves habitability. The planet's atmosphere is held in place by the strong gravitational field, preventing it from seeping away into space as Mars did. Even the most severe stellar flares from the host star, which occurred billions of years ago, could not remove the K2-18b's thick atmosphere. This gravitational advantage applies to the planet's ability to retain water. On Earth, we lose water to space through a process known as atmospheric escape, in which solar radiation breaks apart water vapor in the upper atmosphere, allowing hydrogen to drift away indefinitely. K2-18b's strong gravity precludes this loss, creating a planet in which water can accumulate over billions of years rather than slowly vanishing. The planet's mass influences its internal structure in ways that benefit life. The high pressure at K2-18b's core most likely prohibits the creation of a solid iron core, like Earth's. Instead, the planet might have a water ice core, surrounded by layers of liquid water, hundreds of kilometers deep. This results in a planetary ocean that dwarfs all of Earth's oceans combined, creating a vast environment for life to develop in diversity. But, perhaps most critically, K2-18b's mass lands it in a sweet area known to astronomers as the super-Earth category. These worlds are huge enough to support dense atmospheres and deep oceans. However, they do not grow to the size of gas giants like Jupiter or Saturn. The threshold between rocky super-Earths and gaseous mini-Neptunes appears to be critical for habitability, and K2-18b falls exactly inside this ideal range. The planet's mass determines its thermal evolution. Larger planets retain heat longer, perhaps keeping temperatures toasty for trillions of years, while the Earth's interior is slowly cooling and will eventually become geologically dead. K2-18b's immense size suggests that it may remain geologically active for periods longer than the universe's current age. This long-term geological action may drive the carbon cycle and atmospheric chemistry, ensuring stable conditions for life. The finding of K2-18b fundamentally changes our notion of planetary habitability. We are no longer searching for Earth's twin. We are seeking for Earth's larger, more stable, and longer-lived cousins. In a universe where super-Earths outnumber Earth-sized planets, the galaxy could be filled with worlds where life has advantages we never believed conceivable. Sometimes the most important discoveries come from what isn't there, such as the James Webb Space Telescope's finding of another potentially livable planet. This universe revolves around the star C. Anoel discovered the planet indirectly after noticing a suspicious gap in the debris disk orbiting the young star. This gap, like a cosmic fingerprint, proved the presence of a hidden universe that influenced the construction of an entire stellar system. Debris disks are large rings of dust, ice, and rocky particles that circle newborn stars. These disks resemble cosmic construction sites where planets are still growing, accumulating material from the surrounding debris to become larger and more massive. When a planet originates within a debris disk, it functions as a cosmic vacuum cleaner, removing material from its orbital path and leaving a clear space in the disk. The debris disk around CE Anal is especially stunning when observed from Earth because we see it face on rather than edge on. This gives astronomers a bird's-eye view of the disk structure, exposing characteristics that would otherwise be unseen in edge-on systems. The disk is divided into 3 distinct rings, each separated by gaps indicating the presence of planets shepherding the material into orderly patterns. When Webb turned its infrared eyes on CE Anal, it saw something unusual in one of these gaps, a faint infrared emission that could only be explained by the presence of a previously unknown planet. The object presently known as this world has features comparable to Saturn, but it orbits in the gap between the first and second debris rings, exactly where computer simulations suggested a planet would exist based on the disk structure. The discovery indicates a new method of locating planets. Instead, than waiting for planets to pass in front of their stars or detecting their gravitational effects, astronomers may now identify planets based on the gaps they leave in debris and disks. This approach, known as direct imaging, allows scientists to examine planets that may never transit their stars. From Earth's perspective, this substantially increases the number of worlds we can discover and study. However, the debris disk surrounding CE Anal showed more than simply the existence of a planet. The disk structure shows that this world actively shapes its environment, clearing out material in its orbital path, while also shepherding debris into the ordered ring structure. This planet is not simply orbiting its star, it is actively shaping the architecture of its entire stellar system. This world's temperature of roughly 120 degrees Fahrenheit placed it in the potentially habitable zone, allowing liquid water to exist on its surface. The planet's position within the debris disk also indicates that it is young, probably still accumulating material, and growing larger. We may be viewing a globe in its early phases of development, before it has had time to establish the complex atmospheric chemistry that distinguishes mature planets. The discovery of debris disks suggests that planetary formation occurs continuously throughout the galaxy. Young stars are continuously building new worlds and webs. The ability to peek through cosmic dust allows us to monitor this process in real time. We are not just discovering planets, we are seeing the birth of new worlds. The discovery of life on K218b was only the beginning. As the James Webb Space Telescope continued its scan of neighboring star systems, a pattern emerged that would fundamentally alter our understanding of life in the cosmos. The galaxy contains more than just a few inhabited worlds. It's teeming with potentially habitable worlds, each with its own set of conditions and opportunities for biological growth. Astronomers have discovered nearly 50 habitable planets within a 200 light-year radius of Earth. These worlds range from super-Earths, like K218b, to tiny rocky planets around red dwarf stars' habitable zones. Each represents a different experiment in planetary development, a distinct set of variables that could produce life unlike anything found on Earth. The diversity of these possibly habitable worlds is astounding. Some orbit near to their stars and have thick atmospheres that cause runaway greenhouse effects, keeping liquid water at temperatures that would boil the Earth's oceans. Others live in the far regions of their star systems, kept warm by internal heat sources and thick atmospheric coverings. A handful exhibit hints of worldwide ice covering, including underground oceans, that might house vast ecosystems concealed underneath frozen surfaces. But it's not simply the quantity of habitable planets that's impressive, it is their variety. Different types of stars produce different sorts of habitable zones, each of which favors a particular type of life. Red dwarf stars account for 3/4 of all stars in the galaxy, create habitable zones that last billions of years, giving life virtually endless opportunity to evolve complexity. More massive stars burn brighter and quicker, perhaps favoring rapid evolution and adaptation. The statistical analysis of these findings is astounding. If 50 possibly livable worlds exist within 200 light-years of Earth, the entire galaxy may then be home to billions of planets capable of supporting life. The Milky Way, with its 400 billion stars, may support more inhabited worlds than there are humans on Earth. Each of these worlds reflects a unique approach to the difficulty of sustaining life. Some may have evolved oxygen-rich atmospheres, such as those found on Earth, to support sophisticated multicellular life that breathe and photosynthesis. Others might have created hydrogen-based biochemistry, creating environments that appear completely alien to Earth-based life. Some may have followed evolutionary routes that we have yet to imagine. The consequences for the quest for alien intelligence are significant. If life exists throughout the galaxy, intelligent life may be equally widespread. The radio telescopes scouring the skies for signals from alien civilizations may not have to look far in a galaxy teeming with life. The question is not whether there is intelligent life elsewhere. It's how many civilizations are attempting to contact us, but perhaps most surprisingly, the discovery of several livable worlds shows that life itself may be a basic element of the cosmos. Exactly as stars form, when gas clouds collapse under gravity, life may arise organically wherever the conditions allow. We are not alone in the universe. We are members of a cosmic community of living worlds that spans the entire galaxy. The universe is more vibrant, more than we ever imagined. Water is the universal solvent, the medium in which life may exist. However, the water on K2-18b is not just any water. Water exists in vast volumes and at conditions that dwarf anything known on Earth. The planet's huge oceans, which could be hundreds of miles deep, are the greatest known reservoir of liquid water outside our solar system. The presence of water vapor in K2-18b's atmosphere was one of the first indications that this globe could be livable. When the James Webb Space Telescope examined the planet's atmospheric composition, it discovered distinct signs of H2O molecules absorbing certain infrared wavelengths. However, the amount of water vapor found indicates something remarkable. The planet's atmosphere is saturated with moisture, implying enormous oceans beneath. On Earth, our seas contain around 350 million cubic miles of water, covering 70% of the planet's surface and reaching an average depth of slightly over 2 miles. However, K2-18b's seas might hold 1,000 times more water, resulting in a planetary ocean that stretches from pole to pole and reaches depths that would crush any Earth-based submarine. This isn't just a water world, it's a water world, and the liquid environment allows for evolution on a scale that would be unimaginable on Earth. The chemistry of K2-18b's water is as amazing when combined with hydrogen from the planet's atmosphere. The water forms a solution, which remains liquid over a far larger temperature and pressure range than pure water. This hydrogen-enriched water may host living forms that use hydrogen as an energy source, breathing the water and obtaining energy from dissolved gases. However, the most crucial element of K2-18b's water may be its stability on Earth. Over billions of years, solar radiation breaks apart water vapor in the upper atmosphere, causing our oceans to eventually disappear into space. Earth will someday be as arid as Mars, but K2-18b's powerful gravity and dense atmosphere prevent water loss, resulting in oceans that might last for trillions of years. The planet's atmospheric greenhouse effect maintains the temperature of K2-18b's water at roughly 120 degrees Fahrenheit, creating conditions that are more than just habitable. However, it is actually advantageous to one's life. This temperature hastens chemical reactions and biological processes while remaining chilly enough to avoid the breakdown of complex organic compounds. It's like having a global hot tub that's perfectly tuned for life. Water on K2-18b also plays an important role in the planet's carbon cycle. The vast oceans can absorb massive amounts of carbon dioxide from the atmosphere, thereby regulating the planet's temperature and atmospheric chemistry. This generates a natural thermostat that maintains conditions over geological timescales, ensuring the long-term stability that complex life requires. Perhaps most remarkably, the water on K2-18b could be only the beginning. If super-Earths like this one are ubiquitous throughout the galaxy, the cosmos might be populated with water worlds, where life has had billions of years to develop in marine conditions considerably greater than anything on Earth. The discovery of K2-18b's huge oceans means more than merely finding water on another planet. It's the discovery of a new type of planetary environment in which life could flourish beyond our wildest expectations. Each molecule tells a tale. When light passes through the atmosphere of K2-18b, it bears the chemical traces of an alien world, resulting in what astronomers call a transmission spectrum, a cosmic fingerprint that discloses the planet's atmospheric makeup with remarkable precision. This fingerprint does more than just inform us which gases surround the planet. It tells us whether life is actively altering the chemistry of the entire planet. The practice of reading air fingerprints is similar to cosmic archaeology. Each molecule in the planet's atmosphere absorbs a specific wavelength of light, resulting in dark lines on the spectrum that Webb can detect and analyze. One pattern is formed by oxygen, another by water vapor, and a third by methane. But when the James Webb Space Telescope investigated the K2-18b spectrum, it discovered something new, a grouping of molecules that can only be explained by active biological activities. The atmospheric fingerprint of K2-18b indicates a world in chemical disequilibrium. In a dead environment, chemical reactions would eventually approach equilibrium, resulting in a stable mixture of gases. That does not alter with time. However, K2-18b's atmosphere contains combinations of molecules that should react and vanish, but they remain in vast amounts. This chemical imbalance is the result of life actively releasing gases into the environment. On Earth, our atmosphere is also out of balance. Our atmosphere contains both oxygen and methane, which should react and dissipate. The only reason they persist is that live creatures continuously produce both gases, maintaining the chemical imbalance that defines a living planet. K2-18b shows the same type of chemical disequilibrium, indicating that life is actively influencing the planet's atmospheric chemistry. The identification of dimethyl sulfide in K2-18b's atmospheric fingerprint is the most compelling evidence yet for extraterrestrial life. This molecule is only created by living beings and degrades rapidly in the atmosphere. Therefore, its presence implies that something is actively making it in large amounts. The atmospheric fingerprint reveals not only the existence of dimethyl sulfide, but also its dispersion across the planet's atmosphere, implying that life on K2-18b is not limited to discrete pockets, but extends over the entire planet. However, the atmospheric fingerprint indicates more than just the presence of life. It suggests the type of life that may exist on K2-18b. The high amounts of hydrogen and methane indicate that the planet's life may use these gases as energy sources, inhaling hydrogen and metabolizing methane in ways that are unthinkable on Earth. The atmospheric chemistry indicates a biosphere based on biological processes that are fundamentally different from anything seen in Earth's evolutionary past. The accuracy required to read these atmospheric traces is astounding. The Webb must measure light absorption at certain wavelengths with an accuracy of 1 part per million, detecting molecular fingerprints so faint that they account for only a small proportion of the star's total brightness. It's like recognizing a single person's voice in a crowd of millions, only the voices carrying knowledge about life on another planet. The atmospheric fingerprint of K2-18b will be recorded in history as the first chemical signature of extraterrestrial life. It demonstrates that life does not simply exist elsewhere in the universe. It is actively altering entire planets, leaving atmospheric traces that may be detected over huge distances between stars. The star system surrounding C Anal is a cosmic nursery where worlds are still being formed at only 6.4 million years old. This red dwarf star is still in its early stages of development, encircled by a disk of material from which planets are still forming. But this youth comes at a cost. The tumultuous processes of star and planetary creation produce environments that appear unfriendly to life. It may be necessary for the complicated chemistry required by life. Young stars, such as CENOL, are famously unstable, with huge flares that can increase their energy output by thousands of times over hours or days. These stellar tantrums assault nearby planets with radiation strong enough to remove atmospheres and sterilize surfaces. However, a planet has been discovered in this system. With a surface temperature of 120 degrees Fahrenheit, it appears to have not only survived, but possibly benefited from these violent outbursts. The debris disk around CENOL depicts the story of continuing planetary formation. The disk is separated into 3 separate rings. Each contains a distinct sort of material at various stages of assembly. The innermost ring comprises small dust and rocky pieces that are progressively clumping together to form planetesimals. The middle ring, where the new planet's orbit, has larger chunks of rock and ice that are being drawn in by the planet's gravity. The outer ring includes clean material that has not yet been disrupted by planetary formation. This continued accretion process indicates that the planet is continually developing, absorbing material from the surrounding debris disk and perhaps increasing its mass. Over time, violent collisions between the planet and debris generate intense heat and pressure, which may drive the complex chemistry required for life.